I know a lot of people are interested in science because they're interested in the medical field. So let me give you a little bit of chemistry about the medical field. Did you know that helium, curium, and barium are considered the medical elements? Because in medicine, if you can't helium or curium, you have to barium. All right, welcome to Investigating Chemical Compounds Part 2. In Part 1, we talked about some different types of bonds. We talked about ionic bonds, which are generally between metals and nonmetals, and it's a bond that's formed by the attraction between oppositely charged ions. So with the stair-step line here, the metals are on the left side of it and the nonmetals are on the right side. So an example of an ionic bond could be something like sodium bonding with chlorine, a metal and a nonmetal. That would be an ionic bond. We also learned about covalent bonds. Covalent bonds are generally between nonmetals and nonmetals, a bond formed when atoms share one or more pairs of electrons. So we're talking about bonding something on this right side with something else on the right side. For instance, carbon monoxide, carbon and oxygen bonding together. That would be an example of a covalent bond. Now, in an even more prior lesson, we talked about investigating patterns of the periodic table. And when I was talking about patterns in the periodic table, I brought up the term electronegativity. Electronegativity is how strongly the nucleus of an atom attracts the electrons of other atoms in a bond. So electronegativity is the ability to take or steal electrons from other atoms. And we talked about a trend on the periodic table that at the bottom left corner, this was the atoms that were the largest. Remember, they were very large. They had a lot of electron cloud, and they weren't able to take in new electrons. They were very low electronegativity. And on the top right was the most electronegative. These are the things that would take things the most. So on the left side, less electronegative. On the right side, more electronegative. And as we go up, it increases in electronegativity as well. Now, the difference in electronegativity can be used to predict the types of chemical bonds that form between atoms. So when you have two different atoms, we can take a look at the electronegativity of the two, and we can then make predictions about what type of bond is between those types of atoms. For instance, if we take francium and we take fluorine, these are very opposite electronegativities. And when you have a great difference in electronegativity, the bond is more ionic. So francium fluoride would be a very ionic bond. Now, let's take a look at carbon monoxide, or carbon, and it doesn't have to be just carbon and monoxide. This could be a large molecule with a carbon and oxygen attached to it. So when carbon is bonded with oxygen, they're relatively close to each other. Their electronegativity is not very different. So this would be a more covalent bond. So when we're talking about these types of bonds, what does this mean? And I'm going to show you guys an example with this model here. This oval is going to represent the electron cloud. So we've got two atoms, and we have an electron cloud of the electrons around these two atoms here. And so fluorine, F2, two fluorines, there is no difference in electronegativity in F2. They both have the same exact electronegativity. And so this would be a true covalent bond. But sometimes you have covalent bonds, but you have one thing that's more electronegative than the other. This is called a polar covalent bond. So hydrogen chloride, or in water, that's hydrochloric acid, by the way, has an electron cloud that looks, the electrons are going to be more over on the chlorine side. So it's going to, this is a sigma. This symbol here is sigma, which means partially negative. It's not completely charged, but this side here has more electrons around it. So this side of the molecule is going to be partially negative, and the side where the oxygen is, the hydrogen is going to be more partially positive. So this is a polar covalent bond. In an ionic bond, you have completely negative properties and completely positive properties. So it's not like it's just covalent and ionic, it's a spectrum. It's a gradient. It's not like black and white. There's grays in between, and it moves through like that. So to figure out how electronegative things are, and if things are really covalent or ionic bonds, or polar covalent, we can actually use electronegative values, and some periodic tables have these values on there. And I do have this table on my website, mrrast.com, and I suggest that you print this out for the rest of the lesson, and you should be referring to these electronegative values, especially when you start to do the practice problems that I'll give you later. So you might want to have this by your side when we're looking through some of these questions. But now, let's place the following in order from least polar to most polar. So here's some bonds: a hydrogen to a chlorine, hydrogen to hydrogen, hydrogen to fluorine, and hydrogen to sulfur. How would we know which ones of these bonds are more polar and which ones are less polar? Well, the bigger the difference, the more polar they are. So we take a look at our periodic table and we identify where these are. So we find hydrogen, and it's bonded with a chlorine. Okay, they're all hydrogen bonded with something else. So let's see, what would be hydrogen to hydrogen? That would be completely nonpolar because there's no difference in electronegativity. Hydrogen to fluorine, so fluorine's a little more electronegative than chlorine. And then we have hydrogen to sulfur. So if we're going to put these in order, the least polar would be hydrogen to hydrogen because there would be no difference in electronegativity. Now the other ones are going to be polar covalent bonds. So this would be a nonpolar covalent bond, polar covalent bonds. And so this is 2.1, this is 2.5. So the one that's closest to hydrogen would be sulfur. So after hydrogen, hydrogen would be hydrogen sulfur. And then remember the trend, least electronegative to most electronegative. So then we would go to the right, more electronegative would be chlorine. So hydrogen chlorine would be the third one. And then hydrogen fluorine would be the most polar covalent bond. So it would go HH, HS, HCl, HF. And you actually don't need the numbers to figure that out if you know the trends, but you can use that periodic table on our test. So what do these numbers mean? How do I know when it's polar covalent, and when it's ionic? So when you take a look at these values, when you subtract the difference in these values, if the difference is greater than 1.7, if the electronegative difference is greater than 1.7, then that would be an ionic bond. If the difference is less than 1.7, then it would be a covalent bond. To be considered a nonpolar covalent bond, the difference would have to be less than 0.3. So 0.3 nonpolar, and that's the differences. Up to 1.7 would be polar, and 3.3 would be ionic. So let's take an example here. Carbon to oxygen, a carbon to oxygen bond. Would that be nonpolar covalent, polar covalent, or ionic? So to figure this out, we take the carbon and we take the oxygen. We have 2.5 and 3.5. And so the difference between 2.5 and 3.5 is 1. Remember when we talk about the word difference, there is no negative or positive. If I say, what's the difference between this and that? It's always the absolute number. If I said, what's the change? Change can have a negative value, but differences don't. So don't get caught up on that you got -1 or +1. It's an absolute value when we talk about difference. So the difference here is 1, and 1 is not greater than 1.7. It falls right around here, and so therefore it would be a polar covalent bond. It's greater than 0.3 and smaller than 1.7. What I'd like you guys to do now is pause the video and give these a try. These are determining bond types. So I want you to figure out what is the difference in electronegativity. You're going to need a periodic table that has electronegativity on it. What's the difference in electronegativity of these bonds? And then determine what type of bond are they. Are they polar covalent, non-polar covalent, or are they ionic? Which of the atoms is most electronegative? And what is an example of a name of a compound that has these in there? So carbon and oxygen, you could have put carbon monoxide or you could put CO2. So I would like you to just type online, do a little research, find an element or a compound, I'm sorry, that has these bonded to each other. All right, so pause it and give that a try. Okay, let's take a look at water's charge distribution. This is the water molecule H2O, and oxygen is more electronegative than hydrogen. So therefore, the oxygen side of a water molecule will be partially negative, and where the hydrogens are, which is on another side of the water molecule, will be partially positive. We can represent the difference in charge distribution by something called a dipole moment. This is when a molecule whose charge distribution can be represented by a center of positive charge and a center of a negative charge. We do so with this symbol here. It's an arrow that points towards the partially negative part of the molecule, and it's moving away from the partially positive part. We could put like a plus sign there. So if we take a water molecule, because water is polar, it's got a partially positive and a partially negative side. If we take a water molecule and put it in an electric field, the water molecule will shift. So a water molecule actually turn if it's a magnetic field to the oxygen side, which is partially negative, towards the positive part of a field, and the hydrogens, which are the partially positive side, will go towards the negative side of the field. Ammonia is another polar molecule that has a partially positive side and a partially negative side. It has a dipole moment. The nitrogen is more electronegative than the hydrogens. So we have a partially negative side here where the nitrogens are, and where the hydrogens are on the other side of the ammonia molecule is partially positive. If you put ammonia in a electric field, the positive side of the electric field, the nitrogen will face towards it, and the negative side of the electric field, the hydrogens will face towards it. And here is a dipole moment that can be used to help illustrate that. Now, van der Waals forces are another type of bond. Dipole-dipole forces between neutral polar molecules. So neutral polar, that means polar but neutral. So we're not talking about ionic bonds. Ionic are not neutral. They are positive and negative. So it's neutral. It's not overall charge, but it's polar. Things like what we just talked about, water and ammonia. The positive end of a molecule is attracted to the negative end of another molecule. A dipole-dipole attraction is very weak. So when you have multiple water molecules together, the negative side of one molecule of water molecule will be attracted to the positive side of another water molecule. Most substances held together by dipole-dipole attractions are gases or liquids at room temperature. That's because that attraction is not very strong. That's the attraction between these molecules that make things solids or liquids. In fact, if it's not strong enough, it'll be a gas. When atoms or molecules are attracted to each other, they will turn into, they'll be associated with each other more, and that's when you start to get things become liquids and solids. So these are interactions outside of the molecule to molecules themselves. That's what van der Waals forces are. So the strongest dipole-dipole is called a hydrogen bond. And so again, we're talking about the negative side of water. Water has a partially negative side and a partially positive side. And in a dipole-dipole, the hydrogen is partially positive, the oxygen is partially negative, and so we get this attraction between the water molecules. Remember, this is separate water molecule and a separate water molecule, but they're attracted towards each other, and that's why water, under normal conditions, standard temperature and pressure, is in a liquid state, because this hydrogen bond keeps those water molecules associated with each other. If you heat up water, if you add more energy to it, they can vibrate fast enough where this hydrogen bond gets overcome, and then water will become steam. It'll evaporate. So hydrogen bonds happen between small electronegative elements and water. So things like fluorine, oxygen, and nitrogen, they're on the second period of your periodic table. They have to be relatively small to get this hydrogen bond to work here, and they have to be very electronegative. So hydrogen bonds happen with things that are quite fond. It's very fond to have a hydrogen bond. Fluorine, oxygen, and nitrogen. So if hydrogen can bond to a fluorine, oxygen, nitrogen of another molecule, then it can hydrogen bond, which would be strongest of the dipole-dipole. Another type of van der Waals force is London dispersion forces. This is what happens in a completely non-polar molecule. There is no partially positive or partially negative to it. So something like nitrogen, N2. There's no difference between the nitrogen. So it's a even distribution of electrons. But electrons are randomly moving around. We talked about the Heisenberg uncertainty principle. The electrons are randomly moving around, and so they're not always going to be symmetrically moving around like they're fixed and it's just turning. At one moment in time, you might have more electrons on one side of the molecule than on the other. And at this one brief flash of a second, you can have one side of this molecule become partially negative, while the other side it becomes partially positive. But this is very short-lived and it will bounce back. So this is just a brief moment in time. Think of it that way. Now, if that could happen, if that happens, that partially negative side could push the electrons, because it's negative, and they'll repel and move them to the other side of another nitrogen, or I'm just making an example, nitrogen, N2. And what would happen is you get a partially negative and a partially positive, and they can be attracted together. London dispersion forces are the weakest intermolecular force. This is by far the weakest force that can attract things together. It's a temporary force that occurs when electrons of two adjacent atoms occupy positions to form temporary dipoles, because this could move back and shift it the other way. So what could make a London dispersion happen? Well, one, low temperatures. The lower the temperature, the slower things are going to be moving, and the more likely it is when it does get to get offset into this unsymmetrical distribution, the more unlikely it is to go back. Have you ever heard of liquid nitrogen? Yeah, you've seen liquid nitrogen. They pour it on things and freeze it. You have to get it extremely cold under a lot of pressure, but what can happen is you get this uneven distribution, and the nitrogen can actually create a liquid, but you heat it up a little bit and it's going to quickly go back into a gas. So it depends on the random motion of electrons. Molecules with more electrons will experience greater London dispersion forces. So nitrogen is rather small, but if you've got a large symmetrical molecule, that would more likely be able to experience London dispersion forces than something smaller. Sometimes I kind of think of it like, imagine like a ship, a boat, and there's a bunch of people on it, and everybody is just randomly walking around. But if everybody kind of randomly walks to one side of the boat, it will list to one side. So if you have more electrons, more people on the ship, it could list even heavier. So I think of it that way. The cause for nonpolar molecules to condense and freeze and to become liquid and solid. So this is the reason why you can actually get nitrogen to become a liquid, because of the London dispersion forces. Substances that experience only London dispersion forces will have very low boiling points and melting points. That means they boil at very low temperatures and they melt at very low temperatures. It means they're usually going to be a gas. However, greater number of electrons means higher boiling points and melting points. So everything is unique, and depending on the structure of the compound we're talking about will determine its boiling and melting point. Again, more electrons, larger it is, the more offset it can get, the more imbalance it can get, the more polar it can get, if it got into that situation. So let me clarify something that a lot of people start to get a little confused about. We're talking about different types of bonds, and some bonds are intra TRA, and that would be a bond in the molecule. So here's a hydrogen chloride molecule. The bond between the hydrogen and chlorine, and you guys should know this by now, this is a polar covalent bond. This is a very strong bond right here. But what would make hydrogen chloride associate with another hydrogen chloride. This is called an intermolecular force or intermolecular bonds. These are nowhere near as strong as the intramolecular force. So intermolecular forces are not as strong as intramolecular forces. Intramolecular forces are those covalent bonds. Intermolecular forces are what determine if something's going to become a gas or a liquid or a solid. The stronger the intermolecular force, the more likely it is to become a solid. And if it's not as strong, a liquid, and if it's very, very weak, it's going to become a gas. So that's intermolecular force. So let's go through the different bonds we talked about and talk about the strongest type of bonds to the weakest type of bonds. So the strongest bond is a covalent bond. This is sharing of electrons. When they share those bonded electrons, that is the strongest type of bond. It's a covalent bond. And by the way, of covalent bonds, triple bonds are the strongest. So triple bonds, and then double bonds, and then single bonds are the strongest in covalent bonds. So like the double bond between oxygen, and you have a single bond between the hydrogens here. We could have triple bonds between two nitrogens. And so this covalent bond, this sharing, is very, very strong. By the way, a diamond, you might, sometimes people, I ask this question, do you think you can see a molecule? Most people say no, they're too small to see. A diamond is one molecule. It's just carbon connected to carbon connected to carbon covalently. There is no intermolecular force. It's just one molecule of intramolecular forces, covalent bonds. And that's why diamonds are so strong, because you're not taking little crystals of different things and breaking them apart. The whole thing is one molecule, all covalently bonded. The next type of bond would be ionic bonds. Ionic bonds are very strong, and these are oppositely charged ions, something like sodium chloride. What happens here is an electron leaves a metal or a very non-electronegative element and goes to a very something that's more electronegative, and it makes something positive and makes something else completely negative. One thing's completely positive, the other thing's completely negative, and those opposites attract like magnets. It's strong, but not as strong as a covalent bond. So the next type of bond I'm going to talk about is metallic bonds. Metallic bonds are metals to metals, and here's an example of I'm just showing magnesium. And in a metal, you have all of these cations. What will happen is the metal ion will be positively charged, and the valence electrons are free to move around. But what's unique about metals is they're good conductors of heat and electricity. They can create a current. You can create a current, so the electrons can move in a direction because they're delocalized. They can move across the metal, and by doing so, you can conduct an electric field. The valence electrons that are moving around act like glue to keep the metal together. So that's why metals are malleable and ductile. You can bend them and stuff like that because these valence electrons kind of keep it together in that kind of situation. But if they're moving, they have to go somewhere. They can't just leave the metal. So that's why when we talk about electricity, we talk about completing a circuit. So here we have different metals. We have metal in the wire, and then we have it going across the filament, creating light, and then another wire, and then even across a spoon, another wire. And what's causing this is a chemical reaction right here that's pushing electrons. There's the cell in a battery. There's parts that want electrons and parts that want to give away electrons, and so by completing the circuit allows the electrons to travel around there and slowly start to complete the reaction that's being just waiting inside of the battery. Anyways, metallic would be the third strongest of the types of bonds. Now we're going to get into van der Waals forces. These are intermolecular forces. So now we have different molecules and how they're associated with each other. And the strongest of the van der Waals force, which are intermolecular forces, is dipole-dipole. This is the attraction between polar molecules, and of the dipole-dipole, hydrogen bonds are the strongest of them. So here is an example of a dipole-dipole between hydrogen and chlorine. And hydrogens and chlorines, the hydrogen chloride will associate near itself, can be in a liquid form, with the positive side where the hydrogen is would be attracted towards the negative side of the chlorine. So dipole-dipole would be the fourth and this would be intermolecular. We're not talking about the bond of the atoms. We're talking about the association of different molecules with each other. It's what makes, again, liquids and solids. And the last weakest type of force is the van der Waals force. Intermolecular forces is the London dispersion force. This again is that temporary lopsidedness. This can only happen when you have a lot of electrons and it's really cold. That will increase the likelihood of London dispersion forces making something become a liquid or a solid, making things actually associate with each other. That's why nitrogen is normally a gas floating around. You have to get it really, really cold to make it, and under a lot of pressure, to turn it into a liquid. And that liquid nitrogen is extremely cold. Okay. The book talks about a little kind of lab demonstration, and I didn't think it did a very good job of explaining things personally. So I want to talk about the different things that it's illustrating. I'm going to show you a quick little video that the book offered on these different structures. So they're talking about, the point of this is this analyzing the properties of compounds. The whole point of it is the melting point can be related to the strength of the bonds. The easier it is to melt something, the weaker those bonds are. So the different substances they used was sodium chloride, and we should be able to figure out, and on this test quiz, I will ask you what type of bonds are associated here. So again, you could look up the ionization energy, or electronegativities of sodium chloride, see that it's a very great big difference between these two, and you'll realize it's an ionic compound. So to melt this, remember, ionic was the second strongest bonds. It's going to take a lot of heat. And I looked it up, and sodium chloride has a melting point of about 800 degrees Celsius. So it has to get really, really hot, but then you can actually get molten sodium chloride. I'm not talking about sodium chloride in water. I'm talking about pure sodium chloride, no water, in a liquid form, molten sodium chloride. And that would be at 801 degrees. The other thing they talked about was citric acid, which is C6H8O7. And this is one molecule of citric acid, and this is called a skeletal model. So instead of drawing there's a lot of things here. A skeletal model, they do these little shapes like this, and I'm going to explain this to you. Every time you see an angle here, see these angles? Every time you see a joint, that represents a carbon. So there's 6 carbons. So here's a joint here, and then an ending point. I'm sorry, though. If there's an ending point without another letter, it would be assumed a carbon. So all the ends have oxygens. So anyways, you should have 1, 2, 3, 4, 5, 6. That's your 6 carbons. Hydrogens are usually only displayed when they're associated with something besides a carbon. So the hydrogens connected to the oxygens are here. So there's 8 oxygens. We know that carbon has 4 valence electrons, therefore it's going to have 4 things connected to it. And if you look at this carbon here, you can see the 4 things. You got a bond here, you got a bond here, and you got 2 bonds here. So you do have 4 things attracted to this carbon. But this carbon only has 2. So you have to assume that there's 2 hydrogens here. So if we take a look, there should be 8 hydrogens. We got 1, 2, 3, 4, and we should have 2 more here, 5, 6. This one's got 4, this one's got 4, 7, 8, and this one's got 4. So there's 2 hydrogens here and 2 hydrogens here. Anyways, this is called a skeletal model. How could these attract to each other? Well, look, if the hydrogen on one of the acetic acids attracts the oxygen of another, what type of bond is this? This is a van der Waals force. This is an intermolecular force, but it's a strong van der Waals force because you have a hydrogen connected to an oxygen. And remember, hydrogen bonds are very fond, F-O-N. So hydrogen connected to an oxygen, a fluorine, or a nitrogen will be a hydrogen bond. So this is one of the strongest dipole-dipoles right here. And as such, to melt a citric acid, you'd have to get the temperature to 310 degrees Celsius. Significantly cooler than the sodium chloride, but still very hot. So this would normally be a solid under normal conditions, standard conditions. And the last example that the analyzing properties of compounds is with wax. And a wax molecule is a hydrocarbon that's just carbon, hydrogen, carbon, hydrogen. And so here is a ball and stick model of wax, and we have carbon, 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 just going like that. And these white, that's the blue ones, and the white ones are going to be the hydrogen attached to it. So each carbon has 2 hydrogens attached to it. And this would go on and on and on for one molecule 31 times for the example that the book is talking about. And how do they attract to each other? Well, again, these are covalent bonds. These are intramolecular forces, covalent bonds. These are very strong. But the wax attracts to each other with the intermolecular force, a dipole-dipole. But it's not a very, very strong one. We have a difference between carbon and hydrogen. So let's take a look real quick at the electronegativity difference of that, because I'm curious. So if we take a look, carbon to hydrogen, it's 2.1 to 2.5. So they're very, very similar in electronegativity. You're not going to have very, very much difference in here. So these are very close to nonpolar. It's slightly polar because that would be 0.4, and I think 0.3 was the cutoff for being nonpolar. So it's as nonpolar as a polar covalent bond can get. So because these bonds are not very polar, this dipole-dipole is going to be very weak, and it'll be dependent on a lot of London dispersion forces, but it's so big that the London dispersion forces and the dipole-dipole, because it's so big, can actually keep it as a solid, but wax melts pretty easily. And in fact, wax melts, this wax C31 H64 melts at 68 degrees Celsius. So this is the analyzing properties kind of example that they were talking about here. They take salt, which is the sodium chloride, the wax over here, and the citric acid, put it on a Bunsen burner, and see which one melts first. And that would be pretty much the lab we would do for this section here. And you can see as it heats up, 68 degrees is when the wax starts to melt, and the wax starts to melt. And basically that's all they show in the video. They don't actually get the temperature up to 310. I think that was it for citric acid, where the citric acid starts to melt. So all you see is some wax melting because the Bunsen burner doesn't get that hot for this demo. But you should be able to predict that the wax is going to melt, and then the citric acid will melt, and then the salt, if you were able to get the temperature over 800 degrees Celsius. Yeah, so just take a piece of aluminum foil and divide up the sections. But unfortunately, I was hoping the citric acid would start melting, but I don't see any sign of it melting in this demo that they gave us. So analyzing it on paper seemed to be a little more of value than actually the demo that they showed us here. All right. The last thing we're going to talk about is VSEPR applications. This is valence shell electron pair repulsion. And basically it's the three-dimensional model of molecules using the Lewis dot structure, covalently bonded molecules. So first thing we do is we construct the Lewis structure, which we did in part 1 of this lesson, and then we arrange the bonding lone pair electrons in a space. So we arrange the bonding and lone pair electrons in space such that it minimizes the repulsion. So if you can't put a bunch of bonds right next to each other. If the bonds have electrons in there, they repel each other, they're going to move apart. So we space things out three-dimensionally as best we can. So in a tetrahedral, that's where you have 4 things apart from each other. You might think 4 things apart from each other would be like this cross. You got these 2 vertically and these 2, but in 4 dimensions, it's more of a tetrahedron. I'll talk about that shape in a moment. So the angle in a tetrahedral may vary from 109.5 degrees. So a tetrahedral, it's basically like a tripod, and every angle is 109.5 degrees apart from each other. The difference could be actually smaller in some cases, because what happens is the electrons in a bonding pair, so here is 2 atoms, and the electrons in a bonding pair are going to be between these two atoms. The atoms have a nucleus, so it's positive. The electrons are negative, are going to be between here. In this picture here, X is a little more electronegative than hydrogen, so we have a little bit more of the electrons over on this side here. But if you have a lone pair, that's when you just put two dots on your Lewis dot structure and there's no bond. When you have a lone pair, there's nothing positive over here to stretch it out. So it kind of like takes up more space. It's going to be around this side, because remember I talked about use four sides when you're drawing your Lewis dot structures. So the lone pair is going to kind of be more focused around the atom than if you had a bonding pair of electrons. So an example here, ammonia is NH3. The Lewis dot structure for ammonia looks like this. You have a bond of two electrons between the hydrogen and nitrogen, two electrons between these hydrogens and nitrogens, but these two are not shared with anything else. And so what happens is these angles are actually less than 109.5 degrees because this lone pair, so this is the shape of a tetrahedral, by the way, and these angles are all 109.5 degrees. So when you have it in 3 dimensions, you can actually get it more than 90 degrees apart. This lone pair here would be occupying more of the space and kind of pushing the bottom tetrahedral angles together closer. And the actual angle of the bonds in ammonia is 107 degrees. You don't have to memorize the 107. I would like you to know the 109.5. 109.5 is the angle of a tetrahedral, and you can just say it's less than 109.5 degrees if there's a lone pair there, and I'll give you some examples of that. So so let's do a comparison of 3 different molecules. We've got, these are all tetrahedral in basic shape. We have methane, ammonia, and water. In methane, we have these bonds, and this circle here is kind of representing that it's coming out at you, and these dotted lines are representing that it's going away from you. It's like I said, it's kind of like a tripod with something coming up on there. And they're all 109.5 degrees. They all have the same electronegativity. So it's 109.5 degree, a very nice tetrahedral shape. Ammonia has this lone pair here, which is squeezing down on it, so it's bending these things together, and so this is actually less than 109.5. The actual angle is 107, but you can just say it less than 109.5. And with water, we have 2 lone pairs pushing on that angle even more. So the angle between the hydrogens is actually 104.5 degrees. It's even sharper because of these lone pairs pushing down on it. So let's talk about some different shapes. The first one is if we have no lone pairs, 0 lone pairs, and 2 bonds, this would be a linear shape. Now, pay attention right now. The bonds can be single bonds, they could be double bonds, they could be triple bonds. It doesn't matter. It's just the fact how many bonds. If there's 2 things bonded, that is linear, and it would be a 180 degree angle. That would be the furthest thing away you could get these groups of electrons from each other would be 180 degrees. It would be a line. You could put that on your paper, it would make sense. When you have 3 bonds with no lone pairs, it makes something called a trigonal planar. It would actually be flat, and these angles are 120 degree angles. 120 degree angles, and it would be flat, and this would be 3 bonds and no lone pairs. Again, these could be triple, or couldn't be triple, but it could be a double bond in here as well. It doesn't make a difference if there's single bonds, double bonds, or triple bonds for these models that I'm showing you. The next one is a molecule, and this shape is called bent. Bent has there's more than one bent molecule. When you have 2 bonds and you have 1 lone pair, this would be less than 120 degree angle because this lone pair is pushing more than these electrons are, so it's going to be a little more repulsion here. So this is a bent structure, 2 bonds and 1 pair of electrons. Tetrahedral would be that shape here that we talked about before. Tetrahedral has 4 bonds with no lone pairs, so it's 4 bonds. There's nothing lone on here, and the bond angle of a tetrahedral is 109.5 degrees. Trigonal pyramidal is the next one. So you take that tetrahedral and you take off one bond and you put a lone pair here, and then that's the trigonal pyramidal. So you have 3 bonds, 1, 2, 3, and you have 1 lone pair, and that would make the angle less than 109.5. You take that tetrahedral again and remove another one, and you get bent. This was like the example I showed you before with water. You have 2 lone pairs and 2 bond pairs, so we're based on the 109.5 degree angle again, and this is pushing it in even tighter. So how do we put this together? What kind of questions do you see in chemistry with this, what we just talked about? So draw the Lewis structure, identify the geometric shape and the bond angles for this is carbon tetrafluoride, so CF4. So let's do that right now. We've got a carbon. The first one should be our center of our molecule. So we put a carbon, and carbon has 4 valence electrons. So let's put those apart first. 1, 2, 3, 4. And now we've got 4 fluorines. So let's put those on the 4 different sides of the carbon. And fluorine's got 7 valence electrons. So let's put that on there. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And remember, if they're already paired together, we don't need to connect the dots on those. So let me just take a pencil. So we don't need to connect the dots on these ones because they're already paired. It's the lone electrons that need to find something to pair with. So we do connect the dots here, and let's do it. Let's do it for old time's sake. Connect the dots. La, la, la. Connect the dots. La, la, la. So there you go. So that's our structure for carbon tetrafluoride. So let's take a look here. Well, we did it right. We have a carbon connected to 4 fluorines. Now, this would be a tetrahedral in shape. It wouldn't have been like I drew it with 90-degree angles. And so if you were going to illustrate this in the proper geometry, this angle here is a 109.5 degree angle, but this one here, we can't draw it flat on a piece of paper because it's 3-dimensional. This one here is coming out at us, this fluorine, and this one here is going away from us. It's like I said, it's like a tripod. And if you were going to, if you're going to write this out, you might write it like this. So if I was going to try to write this with the proper angles on here, I would go maybe something like this. So I keep these ones here. And look, I'm not making these 90-degree angles. It's greater than 90-degree angles. And then maybe this one here is coming out at me. So I make a triangle, and I color it in coming out. And then this one's going away from me, and so I do a dot like that. So that's how I would illustrate this kind of more 3-dimensionally. Okay. So draw the Lewis structure, identify the geometry shape and the bond angles for this. So this would be tetrahedral, and you look back in those notes that I just gave you, it has 4 bonds. We're talking about the center atom, by the way, 4 bonds and no lone pairs. Yes, there's lone pairs in this molecule, but the center atom, the geometry of the center atom is a tetrahedral. When you have a huge molecule, you'll have different angles for all the different atoms in there. So with all these examples I'm going to give you, there's a center molecule. So this is a tetrahedral. It's got 4 bonding electrons and 0 lone pairs. So 4 bonds, no lone pairs. And it would be 109.5 degree angle would be the angle for this one. All right. So what I want you guys to do is don't get overwhelmed. Don't get too scared. For these 7, do the Lewis dot structure like you did in part 1. Do the Lewis dot structure for these. After you do the Lewis dot structure, count them up. Take a look at that center one and figure out how many bonds are there, how many lone pairs are there. Based on how many bonds there are and how many lone pairs there are, you can try to identify the name of the shape. So is it trigonal planar? Is it trigonal pyramidal? Is it tetrahedral? Is it bent? Is it linear? And then also identify the angle that it would be. So just look that up. Just do your Lewis dot structure and then look at that table, and you should be okay on that. If you have any questions, let me know. I'm here to help, and I'll talk to you soon.